Most students memorize electrochemistry, but if you understand today's logic, half the chapter becomes automatic. Hello students, let us continue part 2, one short theory part of electrochemistry. I hope everyone watched part 1 and continue part 2. So in part 1, till reference electrodes we completed and continue from there. Today we are going to start types of metal electrodes. So continue here. First I am starting with types of metal electrodes. Types of metal electrodes, the continuation topic after completion of part 1. So everyone pay attention and continue. So types of metal electrodes, here two types we are going to see mainly here. First type, which we call it as metal plus soluble salt combination, metal plus soluble salt. Other type, metal plus insoluble solid, means like a precipitate type, insoluble solid plus another combination, soluble anion. Soluble anion. So metal plus soluble salt, metal plus insoluble solid plus soluble anion. Let us see example under this. Under this particular part, if I take one example, already we discussed even in Daniel cell, like example zinc solid metal combination plus insoluble salt zinc sulfate, which is aqueous. Similarly, examples under second category, we already discussed calomel electrode. Calomel electrode is one of the examples under metal plus insoluble solid Hg2Cl2, which is solid plus soluble anion aqueous. Along with that, one more example I am taking here, which is Ag solid plus AgCl solid plus Cl minus aqueous. Calomel electrode already we discussed. Now we will expand. See, metal plus soluble salt already we discussed in Daniel cell, like zinc dissolved in zinc sulfate type solution. This part already we have done in part 1. Now here we will see about the second example of metal plus insoluble solid plus soluble anion. Let us see here. So under this, I am taking example here, metal plus insoluble solid plus soluble anion. So this particular combination we are taking one example and proceeding further. So observe it everyone, keep heading from your side, then continue. Metal plus insoluble solid plus soluble anion. So example here first I am taking, that is silver example, already we wrote above, we are elaborating now in detail. AgCl solid plus Cl minus aqueous. First if we consider it as, we are considering now it as a cathode. You write like this, as a cathode. We know cathode reduction occurs. So we are referring now the electrode as cathode. So based on that, see the cathode reaction here. At cathode, two reactions occurs. First, AgCl solid dissociate like Ag plus aqueous plus Cl minus aqueous, dissociate like this. For this, if I consider delta G1, similarly second reaction, whatever Ag plus produced in above reaction continued and here gain electron and convert into Ag solid, which I refer it as delta G2. So net cell reaction, after adding both, if you are writing net cell reaction, AgCl, which we know it is solid, plus electron. So net cell reaction, remember, important, Ag solid plus Cl minus aqueous. If I consider it as delta G3, if I take it as delta G3. So now here we know reaction is at equilibrium. It is at equilibrium. So whenever reaction is at equilibrium, we know the formula minus 2.303 RT log Ksp. So first I am writing C here, delta G3 is equal to delta G1 in standard form if I take, or in standard form, delta G1 plus delta G2 standard form. So what is delta G3 here? Delta G3, so I can write in terms of NFE naught cell, because we know delta G is NFE naught cell. There I am writing Cl minus AgCl, it is reduction, right? So in this sequence we write is equal to delta G1, as it is at equilibrium, I am writing like this, 2.303 RT log See, for insoluble solids, we write solubility product. Solubility product Ksp is equilibrium constant only. K is equilibrium constant, we are writing in terms of solubility product. When we use solubility product, whenever insoluble solid given, then we can write solubility product. Okay. Next, plus another delta G2, how we can write? NF E cell. So here it is a reduction part only, we are writing Ag plus 2 Ag. Ag plus 2 Ag, which is delta G2 reaction. We substituted here. So overall, if we modify it and write E naught Cl minus AgCl Ag is equal to here E naught Ag plus and Ag plus 2.303 RT by F, 2.303 RT by F it is, that is Faraday. How we are getting this? We are dividing the equation by minus NF. Here you can specify, divide the equation by minus NF. So if you are dividing by minus NF, overall here we are going to get log KSP. So this particular equation we are getting after dividing equation by minus NF. Okay. So here there is one important fact. This you have to remember. Experimental observed values. Fact number 1. E naught Cl minus AgCl, Ag is equal to, is not equal to E naught Ag plus Ag. In standard form it is not equal, but same if you use in normal form like E, here you specify ECl minus AgCl Ag is equal to EAg plus Ag. After applying Nernst equation we will get this. After applying Nernst equation we will get this, but here it is equal. But here remember, here it is not equal. So this you remember, important, the relation. If it is in standard form not equal, but in regular form under normal conditions it is equal. It's experimental observed values. So you need to remember here. Okay. So here we used as cathode. Now I am writing it as anode. See now. Case 2 as anode. We know anode oxidation occurs. So we are writing now it as anode. So if you are writing as anode, once you see the reactions directly here, so what we can write? Reaction number 1, Ag is solid, here it is giving Ag plus aqueous plus electron. Similarly, second reaction, Ag plus aqueous plus Cl minus aqueous will give AgCl solid. If we join both, again net cell reaction of anode, Ag solid plus Cl minus aqueous giving, it is important for advanced exams, AgCl plus electron, which will get here n is equal to 1 anyway. So net cell reaction at anode. Net cell reaction at anode. See combination here. Overall net cell reaction, remember in both the cases, anode as well as cathode. Observe it everyone. So next moving further. So it is about types of electrodes. Among those electrodes, one example we studied, that is about silver electrode. Metal insoluble solid plus soluble anion. Okay. Next continue some important thermodynamic formulas. Important thermodynamic relations. Keep heading. Important thermodynamic formulas. So important thermodynamic formulas here in relation with thermodynamics and electrochemistry. Because sometime previously they asked even direct questions based on these formulas. You write, just list out, recollect thermodynamics, and I am writing here NF E naught cell, and delta G naught is equal to minus 2.303 RT. You can write it as log KSP, solubility product. Then similarly, delta G naught, decrease in Gibbs free energy, is equal to maximum work done, maximum useful work done, or you can write even E naught cell is equal to minus 2.303 RT by NF, N is number of electrons involved, log KSP. See, log KSP we write when we write if there is insoluble solid, then we use this formula. Temperature coefficient meaning we are relating any physical quantity with respect to temperature. Temperature coefficient, so here we write like this, E cell we are relating with respect to temperature at constant pressure, temperature coefficient of this cell. Next, if I relate delta G is equal to delta H minus T delta S, all are thermodynamic formulas. Here one more important formula with respect to electrochemistry, delta S is equal to NF temperature coefficient dE cell by dt at constant pressure. Another formula, delta G is equal, already we wrote NF is cell, delta S is equal to NF dE cell by dt P. And then delta H is equal to minus NF E cell plus NFT dE cell by dt, dE cell by dt. Okay. Next, delta Cp is equal to, after overall derivation I am writing here, NFT d square E cell double differentiation by dt square. Delta Cp. What is delta Cp? Molar heat capacity at constant pressure. Delta Cp is products minus reactants. Delta Cp here, products minus reactants. Right here, products minus reactants. So these formulas you have to remember, these are in relation with thermodynamics as well as electrochemistry. Write down on particular paper, later you can properly go through those questions related to those formulas. Next moving to electrochemical series. So keep heading here, electrochemical series. So electrochemical series, here we are going to see like cations as well as anions separately. So cations of these metals we are taking here. So here case 1 I am writing electrochemical series based on their reduction potential, top to bottom they are arranged. I am going to give here, first you specify these. So cations of given metals. So cationic series I am writing here like lithium, potassium, barium, strontium, calcium, sodium. This series you have to remember, magnesium, aluminium, zinc, chromium, iron, cadmium, cobalt, nickel, tin, lead. Then followed by hydrogen. Cations of these metals we take here. Then followed by hydrogen. Then what? After hydrogen, like known element, these are copper, iodine, here mercury plus 1 you will get, then followed by silver, then mercury plus 2, bromine, Cl2, after bromine you can write even this one, after bromine you write here platinum, followed by Cl2, Au and F2. See the sequence: lithium, potassium, barium, strontium, calcium, sodium, magnesium, aluminium, zinc, chromium, iron, cadmium, cobalt, nickel, tin, lead, hydrogen, copper, iodine, Hg, mercury plus 1, Hg plus 2, Br2, platinum, Cl2, Au, F2. Sequence you have to remember for cations. So for these cations, whatever we mentioned here, down this series, for cations we mentioned here, see, cations of respective metals. So key points you remember for the given series. Down this series, what we need to compare here, see, SRP value, the standard reduction potential value, increases top to bottom. If SRP value increases, SOP value decreases, If SRP value increases, ease of reduction increases. Ease of reduction increases. Why? Easily undergoes reduction. So if ease of reduction increases, oxidizing power increases. Oxidizing power increases. Reducing power decreases. Reducing power decreases. Top to bottom. So reducing power decreases, even metallic character decreases. Metallic character decreases. See, very important statements we are writing here. SRP increases, SOP decreases, ease of reduction increases, oxidizing power increases, reducing power increases, metallic character decreases. Here, one important statement, SRP value, if it increases, or you can say SRP value directly proportional to strength of oxidizing agent. Most of the students having confusion here, but after watching this video, no more confusion. SRP directly proportional to strength of oxidizing agent. Similarly, SOP directly proportional. If any substance having more SOP easily undergoes oxidation. Easily undergoes oxidation means acts as reducing agent. So you can say here strength of reducing agent. Here you can specify strength of oxidizing agent, strength of reducing agent. More SOP meaning better reducing agent. More SRP meaning better oxidizing agent. So top to bottom, ease of deposition down this series. These are cations, ions of, you can say cations of these metals. Ease of deposition at cathode increases. Ease of deposition at cathode increases. So it is about case 1 like cationic type we gave here. Similarly, you write here for case 2 anions. Case 2, that is anions. Anions only few you need to remember. Commonly used substances like SO4 minus 2, SO4 minus 2, NO3 minus, OH minus, Br minus, sorry, Cl minus, Br minus, I minus. Okay. Here you see down this series. Down this series in this given, ease of oxidation increases and ease of deposition. Down this series it is. Ease of deposition at anode increases. So tendency to undergo oxidation, ease of oxidation increases means tendency to undergo oxidation. So you can write here SOP increases, SRP decreases down this series. Okay. Observe it everyone. Ease of oxidation, ease of deposition at anode increases, SOP increases, SRP decreases. Okay, next moving further. Next, write one small note here. Already we specified about relation. So I can write here ion with more SRP. Ion with more SRP is best oxidizing agent. Similarly, ion with more SOP is best reducing agent. Best reducing agent. I think it is clear to everyone. Very important till here. Any doubt? Okay. Next, proceed further. Next, continuation after completion of electrochemical series. Moving further, examples of electrolysis. Keep heading. Examples of electrolysis. Or electrolysis. So under examples of electrolysis, first of all, here remember anode is, in Daniel cell we wrote different. Here anode is positive, cathode is negative. We wrote even in the beginning of the chapter, anode is positive, cathode is negative. So in electrolysis process, if I take one example first, electrolysis of molten MgCl2. Electrolysis of molten MgCl2. See this? So under this example, electrolysis of molten MgCl2, first MgCl2 break down into Mg plus 2 and 2Cl minus. We know cation move towards cathode. So here I am writing at cathode. Cation move towards cathode, reaction occurs like this. Which one? Cathode, that is Mg plus 2 gain 2 electrons because it is reduction at cathode and forms Mg. Similarly at anode, which is positive electrode at anode, Cl minus 2Cl minus lose 2 electrons and forms Cl2 gas at anode. Okay. Next, electrolysis of concentrated H2SO4. Electrolysis of concentrated H2SO4. So here you take example H2SO4 concentrated by platinum electrode, by using platinum electrode. See, platinum electrode is inert, which will not participate in the reaction, just used as charge carrier. See, for example, H2SO4 splits into 2H plus and then SO4 minus 2. Similarly, H2 also present, so it gives H plus and OH minus. Now, at cathode if you see, reaction you see here, H plus or you can say 2H plus, 2 electrons giving H2. At anode there is negative electrode. Anode reaction you see here, 2 molecules of sulfate, it is concentrated, right? Instead of giving chance to OH minus, you see here, in solution, OH present, SO4 minus 2 present. But whichever is present below in series, see, SO4 minus 2 OH, whichever is below, see, ease of deposition at anode increases down this series. So below is OH minus, but SO4 minus 2 we are showing deposition. Why? Here I will tell you the factor is concentration. Concentration is dominant here. I will tell you here, SO4 minus 2, here it lose electrons and forms S2O8, means 2 molecules combine and 2 electrons. See, this we can write even it as H2SO8. H2SO8 is Marshall's acid, scientist name Marshall's acid, scientist name. So here you remember one statement here, the order of dominance. With respect to order of dominance, whenever there is electrode which is active electrode, then electrode is dominating factor, then concentration of solution, then followed by what else? Concentration of solution followed by relative position in electrochemical series. Relative position in ECS I am writing electrochemical series. So what is the meaning of this? Whatever I wrote here, whenever if electrode is active, electrode itself participate in the reaction. Here you specify if it is active. If it is active, then it itself participate in the reaction. So it is used to decide the selective discharge of cations or anions. Selective discharge of cations or anions. Meaning here, whenever 2 types of cations present or 2 types of anions present. For example, see here, in this solution 2 types of anions present, SO4 minus 2, OH minus 2. Then which ion we need to show at anode? That is decided by of these 3 factors. Electrode is inert here because platinum. Then concentration is dominating. In question you see concentrated H2SO4. That's why the ion with more concentration discharge first. If it is dilute solution, if electrode is inert, then automatically we will see relative position. Whichever is below in series, it undergoes discharge. at respect to electrode. Okay. Next, moving further. See next, laws of electrolysis. Keep heading Faraday's laws of electrolysis. Faraday's laws of electrolysis. Next topic. See, presently theory we are focusing. Next part we are going to see even questions based on all these whatever formulas we wrote. Keep heading Faraday's laws of electrolysis. So first here I am taking first law of electrolysis. Faraday's first law of electrolysis. So according to Faraday's first law of electrolysis, the weight of substance deposited respective electrode directly proportional to Q. Weight of substance deposited respective electrode directly proportional to Q. What is Q here? Q is charge, W is weight. But here we know Q is equal to IT. So further I am modifying, or if you remove proportionality constant, keep one constant here, which is equal to Z and Q. Q is charge, Z is electrochemical equivalent. Electrochemical equivalent. So first, in place of Q, if I write Q is equal to current into time. Q is equal to current into time. So Z equal to W is equal to ZIT. So here Q is equal to current into time. Charge, Q is charge. Z is electrochemical equivalent. It is constant. Electrochemical equivalent. Electrochemical equivalent. So here how you can write? Z is equal to equivalent weight by 96,500. It is charge of 96,500 coulomb. It is charge of 1 mole of electrons. So directly I am writing here formula. W is equal to, final formula what we need to remember, EIT by 96,500. From the first law of electrolysis, this you have to remember. Next, coming to second law. Second law of electrolysis. Second law states that when equal charges pass through different solutions connected in series, when equal charge, the ratio of substances collected near respective electrodes is equal to their respective electrochemical equivalence ratio or equal to their equivalent weights. For example, copper, zinc, if you take, weight of copper by weight of zinc is equal to equivalent weight of copper by equivalent weight of zinc. So respective ratios equal according to given statement. W is weight, Z is electrochemical equivalent, E is equivalent mass. Equivalent mass. See, what is equivalent mass? Equivalent mass is molar mass by n factor. Molar mass by n factor. What is n factor? Already you know, we studied about it. Similarly, here there is current efficiency term, which you can write like weight is equal to EIT. If they ask about current efficiency, then you can include it. Otherwise, we take it as 100% and move further. Here, NEET are representing current efficiency. Current efficiency. So remember, NEET is 1 if efficiency is 100%. Efficiency is 100%. If they ask current efficiency, based on modification of formula, you can use current efficiency NETA we represent here. Okay, and close the note and move further. Next, types of cells. Types of cells. See, first here types of cells, primary cells. Primary cells, see, primary cells cannot be recharged after its usage. Cannot be recharged after its usage. So cannot be recharged after its usage, referred as primary cells because they are non-rechargeable batteries. Example, dry cell, also referred as Leclanche cell. Dry cell or Leclanche cell. So in each case, anode cathode you remember, net cell reaction you remember. In each case, see, anode, in this case anode is zinc container, cathode it is graphite, And here electrolyte. Electrolyte is a combination of MnO2 plus NH4Cl plus zinc chloride plus carbon. Zinc chloride plus carbon, electrolyte. So net cell reaction I am writing here, whichever happens in dry cell, net cell reaction. So net cell reaction, zinc plus MnO2 plus NH4 plus, which we can write as MnOOH. So it is also written as HMnO2, both are same, plus another complex like zinc tetraamine NH3 4 times and plus 2. So it is net cell reaction that happens in dry cell. So one example is dry cell under primary cells. So copy it. Next, moving to after dry cell, mercury cell. Mercury cell. So mercury cell, where we use? Mercury cell used in watches like hearing aids. There we use mercury cell. First you see here anode. Anode is zinc mercury amalgam. Zinc mercury amalgam. Similarly here cathode. Cathode is paste of or mixture of HgO, mercuric oxide plus carbon. Electrolyte. Electrolyte used in this process, it is paste of KOH and then zinc oxide, electrolyte. A net cell reaction. Net reaction if you see here, so net reaction zinc mercury amalgam. Reaction we show like this, zinc mercury amalgam plus mercuric oxide which is solid, zinc oxide solid plus mercury liquid. Mercury liquid. So it is net cell reaction that occurs in mercury. Is it memory based? You have to practice reactions. Next, moving to secondary cells. I am writing here, see, primary cells, then followed by secondary cells. Keep heading. See, secondary cells can be recharged. These can be recharged after its usage. So first example for secondary cell, lead acid battery. Lead acid battery is important. Lead acid battery. So in lead acid battery, what are the components or anode cathode you see here? See, anode cathode you have to remember, important, of each cell. So here anode is Pb, cathode is, so anode is Pb and then followed by cathode is PbO2, lead dioxide, PbO2. Electrolyte. Electrolyte in this process, here you will get H2SO4, 38%. 38% mean, for example, 38 grams of H2SO4 mixed with 62 grams of water. So then net cell reaction you see here, I am writing net cell reaction for lead acid battery. So net cell reaction, where the combination of reaction that happens at anode as well as cathode. See now. So net cell reaction Pb plus PbO2 plus H2SO4 if I write 2 times, giving 2 PbSO4 plus 2 H2O. So this particular reaction occurs, if you observe it, this particular reaction occurs during discharging, different reaction occurs during charging, different reaction. So this particular reaction occurs during discharging, during recharging, opposite reaction occurs. During recharging, opposite reaction occurs. Very important, opposite reaction occurs. Okay. Next moving to another cell, nickel cadmium battery. Nickel cadmium battery. Keep heading. So nickel cadmium battery mainly it is used in like cordless phones. We use nickel cadmium battery also. Like here see anode, Anode in nickel cadmium battery, that is cadmium solid. Cathode is NiO2, NiO2 solid, or you can write even NiOOH, NiOOH. Then electrolyte. Electrolyte in this process, that is KOH, KOH. And net cell reaction. Net cell reaction, if you see, cadmium solid plus NiO2 solid plus 2H2O, which is liquid, giving cadmium hydroxide, which is solid, plus nickel hydroxide solid. Nickel hydroxide, which is also solid. When this reaction occurs during discharging, this particular reaction occurs during discharging. Exactly opposite recharging. You specify occurs during discharging. See, during discharging of cell, meaning whenever we are using the cell, this particular reaction occurs. Okay. Exactly same. Whenever recharging, exactly opposite reaction occurs. Copy it. Pay attention, listen. Next, corrosion. Corrosion of iron. See, corrosion of iron, it is an electrochemical process. Corrosion of iron also comes under electrochemical process. Rusting of iron. See here, during this process, anode is a piece of iron, whatever piece of iron undergoing corrosion. Cathode is, during this process, cathode is atmosphere. Atmosphere, mainly here O2 you can say, acts as cathode. Okay. So reactions you see here now. Reaction, first of all, it is an electrochemical process. Electrochemical phenomenon. So corrosion of iron, you can consider it as electrochemical phenomenon. So reactions you see now. At anode, reaction, that is iron lose electrons, means undergoes oxidation and forms like this. At cathode, reaction is O2 plus oxygen react with H plus 4 electrons and forms H2O. So net cell reaction, if you see, net reaction here, 2Fe plus O2 plus 4H plus giving 2Fe plus 2 plus 2H2O. It is given. So further what happens here, Fe plus 2 further oxidized to Fe plus 3. It is combining with X number of water molecules, and finally we will get Fe2O3 XH2O. Fe2O3 XH2O, which we call it as rust. So here rusting of iron or corrosion of iron is an electrochemical process, whatever we showed. Remember, saline water, or you can say salt in water, can speed up rusting of iron. Very important statement. Reason for this, saline water shows more rate of rusting. Reason for this, salt increases the conductivity of water. Means because of presence of more number of ions, salt can increase the conductivity of water. Whenever salt is dissolved into water, due to presence of more number of ions, water becomes better conductor. So reaction occurs quickly or fastly. Okay. Next, some important terms. Keep heading some important terms. See, few terms already known to you. First, it is resistance. So resistance R. So here I can write resistance R is equal to rho L by A. What is here rho? Rho is equal to specific resistance. Rho is equal to specific resistance, and then similarly L is equal to distance between electrodes. Distance between electrodes. A is equal to area of electrodes or metal plate. Area of electrodes or metal plate. Okay. If you see units of R or resistance, units of R is equal to, here you can write, we know already units of R, that is ohm, or you can write like this. Okay. Next, another term, conductance. See, conductance, which we call it as G, conductance. So, conductance is exactly reciprocal of R, G. So, units of G is equal to, you can write ohm inverse. See, ohm inverse, which you can write even it as Siemens. Siemens, 1 Siemens is 1 ohm inverse conductance. So, another term, specific conductance. Specific conductance we represent by using letter K. So, here K is equal to 1 by rho. R you can write K is equal to 1 by R L into A, the formula based on above terms. But here one important term, new term, which is L by A, which we call it as cell constant. Cell constant, or you can write sigma or G star. Cell constant L by A. So, here units of K. So, what are the units of K here? See, units of specific conductance, or which is also referred as conductivity. Conductivity. So, units of K you can specify like, it is nothing but conductivity or specific conductance. Ohm inverse and then centimeter inverse. Ohm inverse and centimeter inverse. Next term, molar conductivity. Molar conductivity, which we represent like lambda m. So, what is molar conductivity? See here. Molar conductivity is, it is conductivity of VML solution containing 1 mole electrolyte. VML solution containing 1 mole electrolyte. 1 mole electrolyte. So, here the representation lambda m is equal to K into volume in ml. The formula for molar conductivity, V is in ml. So, further if we modify like molarity volume ml, in terms of molarity if we further modify it, the final formula what we need to remember under for molar conductivity, K into 1000 by capital M, where here capital M is molarity. Capital M is molarity. And then similarly units of lambda m. If you see units of lambda m, units important here, ohm inverse, centimeter square, and then mole inverse. Units of molar conductivity. Similarly, if you write another term which is equivalent conductivity. Equivalent conductivity. So, equivalent conductivity we represent like lambda E. Lambda E. So, similarly if I define lambda E is equal to K into VML, or same if I write like above formula, lambda E is equal to K is specific conductance into 1000 by N is normality, which is normality. So, units of lambda E. Units of lambda E. So, there we wrote mole, here we write equivalent. Ohm inverse, centimeter square, equivalent, per equivalent you can write. Okay. Next, here you write one simple note. There is a relation between equivalent conductivity as well as molar conductivity. Equivalent conductivity is molar conductivity by valency factor, or you can say n factor, both are same, valence factor or n factor, molar conductivity by n factor. And we know degree of dissociation alpha, which is equal to molar conductivity at concentration C by molar conductivity at concentration infinite, or you can say infinite dilution. See here, it is degree of dissociation, DOD alpha. Degree of dissociation you can write like ratio of molar conductivity at concentration C. What I wrote here, subscript concentration C at infinite dilution. So ratio of molar conductivity concentration C by molar conductivity concentration, you can say infinite dilution we consider it as, and we will see terms here now clearly. So here I am writing lambda m C is equal to lambda m at concentration C. Infinity is equal to lambda m at infinite dilution. See, infinite dilution meaning V is infinity, C is 0. V became infinity here, C becomes 0. Infinite dilution means more and more water added to that, it becomes more diluted. Okay, and then see next, close the note and write Kohlrausch law. Kohlrausch law, next law, at infinite dilution, the molar conductivity of solution is equal to sum of molar conductivity at infinite dilution, it is conductivity of cation plus molar conductivity of anion. Cation plus anion, that is about Kohlrausch law. One example if I take here, molar conductivity of NaCl is equal to molar conductivity of Na plus, then molar conductivity of at infinite dilution of a Cl minus. Similarly, molar equivalent conductivity if I write, or you write first molar conductivity infinite dilution for MgCl2, which is equal to Mg plus 2, then 2 into Cl minus, because here stoichiometric coefficient 2 Cl minus you will get, right? So 2 into Cl minus. But here you pay attention, if you are writing same in terms of equivalent conductivity, as we know formula molar conductivity by n factor is equivalent conductivity. Here no need to specify. Stoichiometric coefficients. Directly you can write only ion. See here how I am writing. See here I did not write stoichiometric coefficient. If they get cancelled, overall no need to write stoichiometric coefficient here. Okay. Next, applications of Kohlrausch law. Applications of applications of Kohlrausch law. So under applications of Kohlrausch law, the first application, see here, the first application, degree of dissociation is equal to ratio, above already we wrote, ratio of molar conductivity concentration C by molar conductivity infinite dilution. Second application, acid dissociation constant is C alpha square by 1 minus alpha. So in place of alpha, if I substitute the given value, so what we are going to get here, alpha is lambda m C whole square by lambda m infinity. So here you can write like this, another formula. Means if you substitute the value, whatever value we got, so you can write another formula, which is Ka is equal to C into lambda m C square followed by denominator. Second application. Okay. Next, third application, lambda m C at concentration C is equal to, here we know 1000 by molarity. Molarity used if it is, see here m is molarity. Molarity is used if it is lambda m at concentration C. Okay. Similarly, if you are writing like this, if you are writing infinite dilution, at infinite dilution, then we use solubility S. S is equal to solubility. Solubility is written if it is lambda m infinity. Solubility is used in denominator if it is infinite, because infinite dilution you can see maximum amount of solution, or you can say saturated. So here we use solubility in this particular sequence. And remember here solubility product or KSP is equal to product of ions present in the given solution of salt. So KSP general formula I am giving P power P, Q power Q, S power P plus Q for solubility product general representation. For example, KSP of AgCl is equal to, you can write here Ag power, what is P and Q here? See here it is P, it is Q. So Ag power 1 into Cl power 1 into S 1 plus 1. So what you will get here? 1 power 1 only, right? Here you don't need to mention even again about it. Directly you write here. If you take it as, so 1 power 1, 1 power 1, S power 1 plus 1. So here you get S square. AgCl, KSP is S square. Okay. Next. Remember, K is an additive property specific. So K total you can write like this. K total is K1 plus K2 plus K3 and goes on. What is K here? Specific conductance. Specific conductance. For example, if there is K total, so here you can write it as K total for AgCl, you can write AgCl plus K total H2O. K total H2O. Because additive property, you can add it and write. Okay. Next. Next, you specify conductometric titration. See, in 11th class you studied about titration, redox titration. Here just we are showing graphs. If you remember graph shape, that's more than sufficient. In conductometric titration, what we do, titration in which end point is determined. End point is the point where reaction is completed, neutralization done. End point is determined. End point is determined by measuring conductance. By measuring conductance, we determine end point. So one sequence you have to remember for conductance. I am giving one sequence, experimental observed values, OH minus, Br minus, Cl minus, K plus, Ag plus, Na plus, lithium plus. So this particular sequence you have to remember for conductance. So here I am writing, see here, it is conductance sequence. H plus having maximum conductance. So now you focus on titration shape curves. It is based on experimental values, we wrote one sequence. So here see titration of strong acid and strong base. How curve looks, see here. I am comparing all here at a time. And then another case, titration of weak acid, weak base also I am writing. Weak acid, weak base. And similarly, one more part where titration of third category, strong acid, weak base, then followed by weak acid and weak base. We will compare all these together. So titration of strong acid, strong base. As we know here, reaction with respect to strong acid and strong base. So I am writing here strong acid like NaOH, strong acid HCl, strong base NaOH, which will form NaCl and then H2O. Here it is H plus, Na plus. So overall H plus is converted into Na plus, or HCl NaOH converted into NaCl H2O. Right? Overall, ion of high conductivity, somewhere you can start. So graph is between volume of NaOH we are adding to NaCl. So in titration what we do? We take HCl for example in beaker, NaCl we are adding time to time from above. Here conductance graph. See only shape you have to remember, graph shape. Based on experimental observed values they plot it. See here now. For example, somewhere we are starting with here where H plus. So graph first comes down, reaches one end point where reaction done. If you add further NaOH, reaction goes up. Here if I take it as end point, it is end point. Okay, here if Na plus is formed, so after forming NaCl, further if you add more and more NaOH, still due to increase in number of ions, graph increases, end point. See why conductivity decreasing here? As we are adding NaOH, the ions of HCl convert into NaCl because of formation of NaCl. H plus conductivity slowly decreases. After reaching to end point, that is lowest point of conductance, then again after adding NaOH, more and more ions increases. So again graph goes up. See conductivity decreasing because the highest conductivity for H plus. In sequence you see here highest conductivity for H plus. As we are adding more and more NaOH, slowly it is converted into Na plus. First drops and again due to increase in number of ions, as we are adding continuously, it increases. Similarly, second case where it is titration of weak acid and strong base. Weak acid and strong base. Example you see CH3COOH plus NaOH, which gives CH3COONA plus H2O. Okay, here also same volume of NaOH I am taking, followed by volume of NaOH and conductance. Volume of NaOH and conductance. So here see, it is weak acid CH3COOH and NaOH is strong acid. So strong acid can produce more number of ions. So first from anywhere one point we select, slightly comes down and then it goes up. In between you can say anywhere like end point. Only shape you have to remember. If they ask which among the following is weak acid strong base graph, you should be in a position to identify. So here it is end point. End point. Okay, first it comes down and goes up. After end point again further goes up. So for weak acid, so immediately it is neutralized and moves up conductance. And then coming to third type, titration of strong acid and weak base. See, it is like first graph, but the difference is instead of going steep rise, it goes like flat rise after end point. NH4OH, so here you can write it as NH4Cl plus H2O. NH4Cl plus H2O. See how it goes up, see. Here as usual conductance, here you can write it as volume of NH4OH. Every time as we are taking in beaker, adding base from burette. Shape here it looks like this. It looks like this, same like above. But after end point, there is flat increase. After end point, there is flat increase in conductance. Because the weak base cannot furnish more number of ions. See here, after end point, steep rise in conductance, but here flat increase in conductance. Reason for that, because we are adding, what we are adding? Continuously NH4OH from burette. NH4OH can produce less number of ions. That's why slowly conductance increases. And next coming to fourth type, which is titration of weak acid and weak base. Weak acid plus weak base. Fourth one. You take such example, weak acid, weak base, CH3COOH plus NH4OH. NH4OH. Here conductance as usual and then volume of NH4OH. It is similar to second graph, but second graph is exactly like tick mark, but here exactly like tick mark you will not get, like you will get like this. After end point, there is steep increase in conductance, but here as it is weak base, flat increase in conductance observed. So these four graph shapes you have to remember. Once again see, in first case steep decrease, steep increase, like tick mark here steep decrease, but flat increase. Why? Because weak base we are adding, it can produce less number of ions. Next, like tick mark, exact tick mark above, but here it is flat increase after end point. Here it is end point. End point. End point is the stage where neutralization completed between acid and base. Okay, acid as well as base, here neutralization completed. So that is about the entire electrochemistry. We completed entire electrochemistry in 2 parts, like you can say one shot electrochemistry, so that if you refer these 2 parts thoroughly, with more confidence you can solve the questions what I am going to discuss in part 3. Okay, I hope everyone clear with all concepts. Part 1, part 2, once again thoroughly watch it and get ready for problem solving for part 3. Thank you very much.